The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees.
Thank you, Rudy, so much. I also appreciate your leadership in organizing this session, so thank you very much. And I also appreciate the previous presenters. Gustavo really gave a nice lead-in to give kind of an overview of what the committee's been working on. And this work is really focused on walls, masonry walls that are already grouted and reinforced with steel, and investigating adding additional reinforcement to increase the load carrying capacity. And as Gustavo said, this is really focused on more slender walls rather than stocky walls. And I'd like to acknowledge Zuhair Al-Jabari and my colleague Mohammed El-Gawadi as co-presenters here today. So I'll go through the objectives, motivation, introduction, the experimental program, test results and discussions, and some conclusions. In terms of objectives, again, the reason we undertook this work was in the early 2000s, mid-2000s, a lot of repair work was done on unreinforced masonry walls, and in particular slender walls where you don't get that arching action in infill applications, because those were sensitive to extreme events and non-ductile type failures. As the committee progressed and we wanted to expand the document, the next question was, can we include reinforced masonry walls that are grouted? Is there any effectiveness to strengthening the systems? And so we wanted to start to develop a database and have kind of a round-robin work. Under Rudy's leadership, some work's been done at NC State, and I've also worked with Zuhair here at Missouri S&T to help develop more of a database to kind of validate the model that's being proposed in the revised version of the 440.7R document. And again, in this work, we looked at, I'll talk mostly about cementitious-based matrices or binding agents. We saw some presentations on epoxy, but we have looked at different fiber types, different reinforcement ratios, as well as the masonry bond pattern stacked or running to see the significance of those. And again, the 2010 version, as you can see highlighted, clearly focused on strengthening of unreinforced masonry walls, did not address reinforced masonry, so the main motivation here is to help develop a database. Again, what are the differences between epoxy and cementitious material? I always like what my colleague at the University of Miami, Tony Nanny, always says. We have different tools in the toolbox, and so we can pull out different tools. And this is not necessarily saying epoxy-based systems are poor, but looking at the opportunity for other binding agents. And so, there are some limitations with anything that we use. And in the case of the epoxy systems, we have some concerns if it's going to be in a higher temperature environment where the resin may deteriorate. There's also the emissions during the installation if it's an enclosed building. And when you move to looking at cementitious materials, they provide better heat resistance. There's also a level of better compatibility with the substrate material. And generally in the durability testing that we've done at our university and some others, it looks also to have very good long-term durability. So we'll kind of focus within the results presented here on the FRCM system and near-surface mounting using a cementitious-based binder, and you can see some of the components here within the study that we used. And again, if we're talking about near-surface mounting, we're talking about providing the reinforcement in the form of a bar or strip near the surface in a slot that then is bound with a cementitious material in this case, or externally bonded to the substrate in the lower case. And we're just marrying two different materials here in terms of the fiber and the matrix. And this just sort of shows you the installation processes from left to right. On top, the externally bonded PBO system, and on the bottom, an example of the near surface mounted installation process. In addition, here you can see the test walls. We actually had a certified mason come in, as you can see on the left images, that actually did the construction of the wall and then grouting of the walls with the steel reinforcement in them. And our overall program to help develop the database included systems with both epoxy and cementitious. You'll see the red box on the bottom. I'll just be showing some of the results on the cementitious system, both with the NSM and the externally bonded. The main point here is that we looked at control specimens with a running bond, a stack bond, and then we looked at varying the reinforcement fiber, carbon or glass, the width of the sheet, or the number of the bars in terms of the near surface mounting to develop several variables within the study. And we also did, not presented here, but we also had a series, as I mentioned, with epoxy, looking at similar variables within those systems. And then finally, also not presented here today, is we also took a number of these walls, put them in an environmental chamber, subjected them to high temperature, low temperature, high humidity, and also looked to see if there was any dramatic environmental impact, but not presented. I just want to give you an idea of the overall tests that we have done in this phase. Of course, we looked at characterization of the materials used, from the grout to the unit of the prisms to the mortar, and also on the composites, so of course to characterize it. What I'll mainly be showing you is the experimental results today, but we are working on some of the analytical studies, and then we hope to pool data from the various studies that have been done and look at the calibration of the 440 document. Again, this is just characteristics in terms of the materials used, as well as the concrete block, the mortar, type S mortar, and so forth, just to give you an idea of the material properties. In terms of testing, what we've traditionally done for out-of-plane testing is, like you saw in one of the previous examples, is we usually have tested in the vertical direction against a strong wall using an airbag. But since these are reinforced with steel and fully grouted, in our case, the airbag system that we've used was not really feasible to generate the load to fail these specimens. So consequently, we tested these in a horizontal position, and since they were fully grouted, again doing a 4-point load test, it's a little less sensitive than an ungrouted wall, where it's a little bit more important to have kind of a uniform load during the test. So we did test this, as you can see, in this configuration here, and that's specifically why. In terms of loading protocol, we used a displacement control in 0.05 inch per minute increments, and we did cyclic, so we could sort of go back and look at the stiffness degradation and some of the aspects on the cyclic loading that I'll show you here in a couple of moments. And we did do duplicate cycles, so we did 2 cycles, and we wanted to look at the loading loop and the unloading loop to look at the area between those two, sort of the energy within the system, in a pseudo-seismic type test to sort of see what the loading and unloading curve look like in a 2 loading cycle. So I'll show you that. So let's get to some of the results here. First, we'll look at the effect of the type of fiber, and you see that on the left, the near surface mounting, as you might expect, the carbon has higher tensile capacity over the glass, and we do see more capacity generated, but we do see, in terms of the bars, once we get a debonding failure, a sharp drop off in the load. You would normally expect that to sort of come down to the control specimen, which is the blue line on the bottom. In some cases, as you lose masonry around the bar and the debonding, you have a little bit greater stiffness degradation. But you can definitely see that there is actually an impact by applying composites on an already steel internally reinforced member. On the right, you see the FRCM system, and there you can see quite dramatic improvements, almost doubling of the capacity in the case with anchorage. So in one case, we anchored the edge, both edges of the reinforcement strip, and the other case we didn't. So you do get debonding. That anchorage definitely helps to improve the ductility of the system. In terms of the bond pattern here, if you look on the left, you see a little bit more capacity with the running bond over the stack bond but they're fairly similar, and this is pretty consistent with epoxy type tests and similar with the externally bonded FRCM system. We do see, again, an improvement there. We take a look at the effect of the fiber reinforcement ratio. As you increase or double the reinforcement, you don't necessarily get twice the capacity. So there is a sensitivity in terms of when the bar starts to debond in the near surface mounted. And so that's a factor in terms of how much additional capacity you'll get. However, in the FRCM system, externally bonded, we do see quite a significant increase of 1 ply versus 2 plies. And then as you increase the reinforcement ratio, of course, you may go to another type of failure mode. For example, you could have a shear failure near the boundary zone. So you have to be careful about analyzing that aspect of it. Stiffness degradation. So here we're looking at stiffness at a particular point versus the number of cycles. And you can see the control specimen. It's linear elastic. So right here is first cracking on the control specimen, and then you get kind of a nonlinear degradation there as cycles increase. Same thing over here with the externally bonded. In the case of the strengthened ones, you have an increase in stiffness, but as it starts to debond and you start to lose stiffness, you start to get more cracking in the bed joints and so on. You start to decay at a quicker rate as you increase the cycles there. But you see the increase in stiffness initially. If we look at the residual displacement, this is after loading and unloading. In the case of the near surface mounted, up to about 2 3/4 or 2.75% drift ratio, you see that it's actually increased, and at that point it reverts back to kind of the base masonry wall system. For the FRCM system, we're looking at about 1.75, but it's marginal in that case in terms of residual displacement. When you look at energy dissipation, this is the area in terms of the loading and unloading. In both cases, we see an improvement there, but most notably, as we provide anchorage, you can see that you can really sort of push the energy dissipation in terms of the wall system. So, as shown earlier, anchorage, if you're able to develop a efficient detail for anchorage, you can get better bang for your buck out of the system. So just to sort of look at normalizing the residual displacement and the energy dissipation, those two things we just looked at, and sort of comparing it to the controlled stack bond pattern, that's kind of the weakest performing. You can see in all these cases, except one here, generally see an improvement of these systems, which is a positive. This is difficult to see, but it goes through the failure modes, and generally what we see in most of these are debonding. In the case we were not able to rupture any of the materials per se to get full capacity. And that's one of the reasons the design standard has a knockdown sort of factor or calibration factor for the strain level you can develop into the material. And this just sort of shows some of the slippage of the PBO fabric and so forth in modes. So just to sort of wrap up with the conclusions here, we did see that it did significantly, the strengthened reinforced masonry walls were improved. They were affected by the type of the fiber, including the GFRP and the CFRP. The flexural capacity was increased anywhere from 131 to 162 for the NSM, or 132 to 197. So it was very effective on the geometry of the walls that we looked at, which was very good. I wasn't so sure how much additional capacity we would get out of these systems. The stack and running bond were fairly similar, as you saw, a little bit better in the running bond pattern. The initial stiffness was greater with the strengthened specimens, as you might expect, and we saw that the control specimen behaved in terms of stiffness retention that we talked about. It was a little bit improved, as well as in the residual displacement up to drift ratios, as mentioned, at the 1.75% and the 2.85%. So using 1 bar of CFRP, the energy dissipation improved by 27%. Is about the same in the case of 2 bars, and we went up to as much as 55% with the 2-ply PBO without the anchorage, and you saw the one with the anchorage was actually the best. And I'd like to thank Midwest Block and Brick for donating the block, Rodil for donating the PBO fabric and the materials, and Hughes Brothers, I don't know if Doug's here, but greatly appreciate the donations to help make this possible. So thank you for your attention.
Can you describe the cementitious material you use?
For the externally bonded, it's a proprietary system that developed in Italy. Perhaps some others are more qualified to talk about it, but it's a cementitious-based system. It has small discrete fibers in it as well that sort of helps improve the performance of the system. That's about my...
Polymer modified properly?
I'm not sure. I'm sorry. Anything else?
I just have an observation I'd like to make as
sure.
well. So post failure, the response of the wall should revert back to the original reinforced masonry capacity. And it's always interesting for me to see how much variation there is when we're dealing with the reinforced masonry, with that steel bar being at mid-height.
Right.
It's actually very sensitive to deviation from that location. And also just the inherent variability when we're dealing with masonry.
Yeah, and the other thing too is, in particular with the near surface mounted tests, the cementitious product actually works very well, such that some of the failure of where the debonding migrates into the substrate. So as you start to lose sort of some chunks of the cross-sectional mass there, that's why you start to see even more degradation in it, to your point, Rudy. So, okay, thank you very much.